In one of the previous videos, I stated that if f is any standard function from the course, such as a polynomial, an exponential function, or a log function, and if f is defined at a point a, then the limit of f as x approaches a must be equal to the value f of a. This property of the limit being equal to the value is so special mathematicians have decided to give it a name, continuity. In other words, any function f of x is called continuous at x equals a if the limit of f as x approaches a is equal to the value f of a. Geometrically, this means that the graph of the function doesn't have a hole or a jump at x equals a. Indeed, a hole at x equals a not only denotes a limiting value at the hole, but also that the actual value of the function is something other than this limiting value, which violates the criterion of continuity. A jump at x equals a would mean that the left-hand and right-hand limits don't agree, which would violate the criterion that the limit at x equals a even exists in the first place. So, geometrically, what this means is that the graph of a continuous function can always be drawn without lifting your pencil. With this understanding of continuity, lots of functions are continuous, including the standard ones that we mentioned earlier. Functions that are more difficult to judge as continuous are ones with weird behavior, such as this piecewise function. Both pieces are defined using the standard ones, which suggests both pieces are continuous wherever they're defined. But the difficulty comes in at the point where the pieces are supposed to match up with one another, that is, at the point x equals 0. At this point, it's not so clear whether this function is continuous. Remember that what we have to check for continuity is whether the limit of f as x approaches 0 is equal to the value of f at 0. In particular, both of these quantities, both the limit and the value, have to exist. And we claim that for this example, one of them fails to even exist. Certainly the value of f at 0 exists because it's just the relevant piecewise definition at x equals 0, which is 0 squared plus 1, or 0. However, the limit doesn't exist because we claim the left-hand limit and the right-hand limit don't agree. Indeed, if we look at the left-hand limit, this is the limit where x goes to 0 from the left, meaning that it's the limit of the upper piece of the function as x goes to 0, which is 1. However, for the right-hand limit, we use the lower piece, and we take x to 0 to get the value of 5. Since the left-hand limit doesn't equal the right-hand one, we conclude that the double-sided limit doesn't exist. For this reason, the function fails to be continuous at x equals 0 because it fails to even have a limit there. The region of continuity of a function refers to the set of points where the function is continuous. In this case, the region of continuity is the set of points except x equals 0. In terms of interval notation, this is the union of minus infinity to 0 with 0 to infinity. This region of continuity is especially apparent from the graph, which, according to its piecewise definition, is a parabola to the left of 0 and a line to the right of 0. One particularly highbrow way of thinking about continuity is that it allows you to push limit symbols through functions. That is, if the limit of g of x as x approaches a equals L, and f is continuous at L, then the limit of the composition is equal to f of the limit. In other words, when f is continuous, we can push the limit symbol inside and outside of f without any concern. Thinking in terms of a diagram can illustrate the significance of this particular result. Starting with g of x, we could first apply f to get the composition of f composed with g, and then we could apply the limit to get a value. On the other hand, if we started with g of x, we could have first applied the limit to get L, and then applied f to L to get another value, which might be different from what we did before. What the result says is that when f is continuous, these values are the same. In other words, the order in which we do these actions, of applying f or applying the limit, doesn't matter when f is continuous.